Hi, I'm Maine and this is Lapse Laboratory. Today I'm going to show you how I turned this ordinary chicken egg into these, using only vinegar, corn syrup, and thyme. To do that, I'm going to dissolve the shells with acetic acid, then pull all the water out with corn syrup. Here's how I did it, while getting some pretty cool time-lapse shots in the process. I measure the size of the egg before dissolving their shells in vinegar to look at the effects of osmotic change and pressure put on the membrane, because the egg is going to expand during this process. I wasn't sure how much space the egg needed to expand, so I started off with one of the smaller beakers that I had available and put it under my dissection microscope with a camera mounted on top to try and film and show the shell dissolving. The shot ultimately didn't work out, but I was able to learn more about macro photography for future projects. You can see in the shot, as soon as the egg is put into the vinegar solution, the CO2 bubbles are formed around the outside of the egg. Because the bubbles are forming on the surface, they cause the egg to become buoyant and float in the vinegar. This pulls the egg out of focus for the microscope and pushes the egg into the sides of the beaker, holding a portion of the egg out of the vinegar. It also creates this egg foam on the surface of the liquid as the CO2 bubbles trap material and minerals in the eggshell and float to the top. I found it interesting that the reaction produced such a large layer of foam on the surface. The acetic acid formed a number of crystals at the direct center of the egg where it had floated out of the vinegar. These crystals would end up showing up later in some time-lapse shots as part of this project. I realized that the beaker size was going to be an issue with this shot, so I let the solution evaporate until the egg was almost entirely no longer submerged, just to see how much of the shell would be dissolved. In the time-lapse shot, you can see the egg begin to float and press against the sides of the beaker as it expands. If you look just to the right of the 120 milliliter line on the beaker, you can see the CO2 bubbles being pressed against the side of the beaker before the egg expands into the side of the glass. By the 24-hour mark, the egg is firmly pressed into the sides of the beaker as the submerged portion of the egg continues to expand. The surface of the egg becomes exposed to air and the liquid level in the beaker drops. The water in the vinegar continues to evaporate, and where the egg is submerged continues to cross the membrane and enter the egg, further lowering the level in the beaker until almost the entire egg is no longer submerged. The top of the egg and the sides of the beaker had an acetic acid precipitate, and that foam mentioned earlier dried out, forming an almost spiderweb-like sticky layer out of the liquid. It balled up almost exactly like a spider web when I scraped it with a stick. You can see the egg is kind of pressed in place here on the sides of the glass, even though the entire thing is out of the vinegar at this point. It was kind of hard to tell exactly how hard I had to press to unwedge the egg from the beaker. I didn't want to rip the membrane or damage the egg before I got it out. It was interesting to see the pigment and the thin brown layer of shell left behind in the glass after being in place for a few days. The brown layer of the eggshell just sloughed off when I touched it, and it was extremely thin on the surface of the egg where it was present. The brown material had a little bit of a grit to it, but the surface of the egg and the white parts of the egg were extremely slippery and bouncy. I only had to barely brush the brown material in the egg to remove it, but it did require contact to remove. I'm not exactly certain what in the eggshell is causing this to happen, but I did specifically choose brown eggs versus something like a white egg because I thought the brown eggs would show up better on camera and be easier to see. I thought that was a neat byproduct of this choice.
So because the beaker wasn't big enough, the eggshell actually washed off and I got pressed into the beaker, and you can see on both sides that the shell of the egg pushed into the beaker and came off in the acetic acid. The egg has a fair deal of squish to it. You can still see the shell because the top of the egg wasn't submerged for a huge amount of time in acetic acid. It's still hard, but a lot of the shell has just completely sloughed off and been dissolved by the acetic acid and the vinegar.
You can see and hear a little bit of that texture I was talking about in the brown material in this shot. The eggshell comes off pretty easily from the inner membrane of the egg, but I'm still being very careful to not puncture that membrane because the egg is so soft. I don't know what it'll take, and if one of the sharp pieces of the egg would accidentally be able to puncture that membrane more easily than I had expected. You can see here just how thin the remaining eggshell is on top of that membrane and the amount of bounce and spring the egg has in my hand. Overall, as far as the measurements go, we have about a 6.9% difference in the length and about a 10.6% difference in the width.
So with any good science project, you take what you learned from the previous one and you apply it to the next one. The beaker was too small previously, 150 ml beaker, the egg pushed into the side, so I'm gonna get a 500 ml beaker now. And because the egg floated to the top, I'm gonna float a 250 ml beaker on top of that.
I'm using the same 5% concentration of vinegar here that I used in the previous shot. I really want to make sure that the entire egg stays submerged the whole time the shell is dissolving, so I'm not left with a lot of those shell fragments that I saw at the end of the first experiment. When you design an experiment, sometimes you overlook basic things without reviewing them. For some reason, because the egg was floating, I thought putting a layer of oil on top would change the fluid density and prevent the egg from floating to the top. But obviously oil is lighter than water, so the egg being less dense than the water due to the buoyancy of the CO2 gas being created, floated the entire egg through the vinegar and oil. So I quickly decided to remove the oil layer and just settled with keeping the egg submerged using a beaker partially filled with water to weigh it down. I also put a stir bar on the beaker to try to move the solution around and potentially get some of the bubbles trapped on the surface of the egg to detach and provide the surface of the egg better contact with the vinegar. This shot was cool because you can see the non-soluble parts of the eggshell being pushed off the membrane of the egg while the egg expands and the shell is dissolved. Here are a few real-time shots of that process that show the egg throughout being submerged from a few different angles and time points. The shell is being dissolved because calcium carbonate, the main component of eggshells, and acetic acid, the main acid in vinegar, react to form calcium acetate, water, and carbon dioxide gas. And because the shell is mostly calcium carbonate, it reacts nearly completely with the acetic acid in the vinegar to dissolve away.
One thing I found really interesting in shooting this is that the eggshell seems to have a membrane on it that's not calcium carbonate that didn't get dissolved by the vinegar.
Taking some measurements of this egg after the shell has been completely dissolved, the egg now has a 5.8% increase in length and a 13.1% increase in width, 2.5% wider than the previous egg, but approximately 1% less expansion in length. Here you can see all the insoluble parts of the eggshell, as well as the water and a little bit of the oil that I was unable to get out of the solution. I kept the stir bar at a low setting for the time-lapse shots, not to jostle the egg around too much, but even at a medium speed, you can create a large vortex in the beaker, and you can see how quickly the insoluble shell pigments move around with the speed turned up. If a 5% solution dissolved the shell, let's see what a 75% solution of acetic acid does to the shell. You can see that the 75% solution here is a different color than the 5% solution from earlier. I covered the beaker because the fumes coming off the setup were very strong. I turned on the stir bar, but then immediately realized that it was going to crack the egg because the egg didn't float when I put it in. I got pretty lucky here that the stir bar didn't crack the egg and ruin the very limited amount of acetic acid at the strength that I had. Due to the high concentration of acetic acid, this egg didn't get those nice, smaller, uniform bubbles and barely floated out of the vinegar at all. In under 8 hours, it bleached all of the brown color out of the eggshell, and this time didn't leave any of that brown membrane material that the 5% solution did. Oddly enough, it did change the tint of the entire acetic acid solution to a light pink hue, and I was surprised how quickly the bubbles dissipated and became very irregular around the egg, with almost all the bubbles remaining concentrated at the top of the egg surface. I used a macro camera positioned to the side of the egg to determine how long to allow the egg to remain in solution. The camera lets me preview the shot as it's happening and allowed me to see the reaction slow down. This camera also gets used later in filming during the shrinking of the egg. I stopped the shot once the rate of bubbling significantly slowed down and the existing bubbles stopped increasing in size. When possible, I try and use this camera in my time-lapse projects to help me know when the subject I'm filming stops changing. I captured this from a few different angles, and from this overhead shot, you can see that within the first few hours, the CO2 bubbles have a somewhat uniform distribution, and then by hour 8, they begin to become non-uniform in size and distribution. Another interesting side effect of the bubble distribution is that it resulted in only a small portion of the egg floating out of solution. When the egg breaks the surface of the vinegar, you can see that the top portion looks hard-boiled. The high strength of the acetic acid essentially rapidly pickled the raw egg while dissolving the shell. Because the shell is so rapidly dissolved, the acid can permeate the egg membrane and quickly cross-link the proteins in a similar way to hard boiling, which is why the egg looks hard-boiled here, because the strong acid has done functionally the same thing. Acetic acid is used in a laboratory setting when working with electrophoresis gels because of some of these same properties. I initially didn't realize that the shell had been dissolved as quickly as it had, and thought that the brown pigment of the shell had just been removed or bleached away. When watching back the time-lapse footage, it becomes clear that the majority of the time that the egg was in the high-strength acid, it was chemically pickling the egg, and that some of the bubbles were originating from inside the egg and not the surface like the previous eggs. The 75% acetic acid also appears to have completely separated the internal shell membrane, which is why some of the bubbles appear trapped between a layer of the egg and under other bubbles. Here's a close-up of the egg in the vinegar right before it was removed, and it actually looks almost exactly like a pickled hard-boiled egg. When the egg was removed, it was very slimy, and you can see the membrane material present in the beaker and on the watch glass. I'm not sure if you'd be able to call it a raw egg still, but technically it hasn't been cooked with heat. The smell coming off the egg and the beaker is intense, which is why I quickly covered the open beaker once I removed the egg. In this solution, the egg only increased approximately 5.3% in length and 4.2% in width. The highest strength acid actually resulted in the lowest percent change in size overall. The egg is incredibly slimy and feels almost like it's covered in mucus every time you pick it up. You can see a little bit of the outside of the membrane present in the watch glass and in the beaker here with the stir bar. Even covered by the watch glass, the acid is still extremely strong up close. The shellless eggs we have now have an increased water content, and I want to get that water out.
So I've got some light corn syrup.
To do that, I'm going to cover the shellless egg in corn syrup. I chose light corn syrup here to make the reaction easier to see. The reason that the egg expands in size during the vinegar step is because the solutes in the entire solution, both inside the egg and inside the beaker, are trying to equalize the osmotic concentration across the egg's membrane, which is permeable to water, but not a lot of the larger materials and solutes that are present inside the egg. As a result, once the shell is dissolved, the concentration of water inside the egg is lower than that of the beaker solution because the egg has more solutes present inside that can't cross the membrane. As a result, because the water can cross the membrane, it floods into the egg, expanding it. Because the cornstarch is so high in solutes, water rushes across the membrane in the other direction from the egg to the corn syrup side in an attempt to equalize the osmotic concentration across the membrane, resulting in the egg shrinking and deflating as water rushes across the membrane. The speed that this occurs was fairly quick, with the majority of the solution equalizing in the first 8 to 12 hours, but I left the solution in place more than double that time just to try to remove as much water as possible. At this point in the shot, you can see very little size change hour to hour. From this close-up shot, you can see how much the egg has pulled in and that the previously expanded membrane has deflated to a point that it's no longer self-supporting. You can also see a bit of the brown eggshell pigment that is more visible now that the egg has decreased in size. It's a bit hard to see in this footage, but there is a slight separation in the beaker liquid between the less dense water from the egg and the denser corn syrup.
So it's been a couple of days, and luckily with this camera over here, I can actually see the time lapse as it's recording. And I can see that the water stopped coming out of the egg, and so it's probably as desiccated as it's going to be. Not sure if you can see this, but almost all the liquid inside of the egg is completely gone. But the yolk inside is still hard. So I'm actually holding it by the yolk here. I got the calipers out to do a measurement, but because it's just a single kind of bag, I'm actually not really certain how I would even measure how much the volume has changed of the egg.
The whole thing pretty much squishes in completely, so I'm being pretty careful here not to break the membrane with the edge of the calipers because they come to a little bit of a point. Overall, I didn't think these measurements were that useful at this stage, and something like a mass would have probably been a better understanding of how much the size had changed. But because I didn't take a mass initially, it wouldn't have been a useful metric at this point of the tests. Definitely another learning opportunity for future projects to improve those. You can see some of the leftover eggshell materials and debris that have fallen off of the membrane as it deflated in the corn syrup. There's also this unique, incomplete mixing between the two liquids that was harder to see in the previous shot.
The corn syrup is slightly less viscous, and you can see a little bit, I'm not sure if the camera will pick it up, you can see the water incompletely mixing with the corn syrup. once I'm trying to stir it up. The liquid still does have a really faint smell of vinegar, but not nearly as much as the egg when it came out of the beaker in the first place. So this is the egg that was in the 75% vinegar and still has a super strong vinegar smell. It essentially pickled the entire egg in the vinegar solution. This was a raw egg when I put it in initially.
Still technically a raw egg at this point, but I think because of the cross-linkages of the proteins, it would be hard to call it that now, because it's essentially been chemically cooked. This egg took a lot longer for the water to equalize because the water is more trapped within the more dense protein of the egg white. There isn't essentially a membrane-filled bag for the concentration gradient to pass over, and the equalization has to happen across a much denser surface. The 5% acetic acid egg mostly equalized in a bit over 12 hours, whereas this egg took over 230 hours. I decided not to shrink the first egg where the shell didn't come off all the way because I thought these two eggs, both the 5% and the 75% egg, both demonstrated what I was trying to showcase in this experiment. I thought it was interesting that the egg yolk made up a much larger percentage of the final desiccated egg, with most of the water being removed from the egg white overall. I'm guessing this is because the egg yolk contains, by percentage, much less water than the egg white, so you can see here in the final shot that the composition between both parts is close to 50-50. I'm just using water in this larger beaker here to clean off the egg. I'm trying to get all the corn syrup off before I handle it more because it's super sticky and hard to clean. Overall, the total change in length from the starting egg is 24.9% and a 30.1% change from the vinegar to the corn syrup. The width total change is 23.6% and a 27.7% change from the vinegar to the corn syrup.
The egg is super hard.
It's a bit hard to see with the glove, but I'm actually pressing fairly hard here with my hand. I can deform the egg white very little pressing into it.
The only piece that's even mildly still kind of squishy is the yolk.
Here you can see the used corn syrup from the 75% acetic acid test being mixed with the leftover corn syrup from the 5% acetic acid test. I thought it was interesting to see how the liquid separated and then became a somewhat homogeneous mixture. It was interesting to see the different speeds that the bubbles moved through the denser corn syrup at the bottom and then began to move faster as they moved through the less dense water towards the top of the separated viscous liquid. As the liquid continues to separate, you can see a more uniform distribution of water and corn syrup, resulting in an almost linear speed increase of the escaping bubbles moving from the bottom to the top. The heavier and more dense corn syrup poured into the top is separating down to the bottom, and the less dense water that has been pushed down by the introduction of the corn syrup is moving back to the top. Because one of the main points of this entire project was to film vinegar and acetic acid dissolving eggshells, I thought I would take an entire beaker of eggshells and fill it with 5% vinegar in order to look at how the eggshells dissolve. I thought this would just result in the membrane inside the shell being left intact after the eggshell had been dissolved away. As soon as the vinegar hits the eggshells, it begins to rapidly bubble, and this timescale for this shot is in minutes. You can see how quickly nucleation begins to occur, and the acetic acid begins to react with the calcium carbonate of the eggshell to produce carbon dioxide and a large amount of foam. You can see how quickly it floats all the light eggshells up completely out of solution. This actually ended up being a problem because the water in the acetic acid solution that was present on the eggshells that were out of solution eventually evaporated off, and it no longer dissolved the shells. I was a little surprised how quickly this reaction took place and how much of the entire eggshell mass was pushed out of the beaker. I hadn't accounted for the significant difference in weight between an intact whole egg versus just the shells themselves, and considering that the surface area of an eggshell is enough to float an entire intact egg with this reaction, this is something I probably should have anticipated. So with this project overall, we have a lot of takeaways for things to consider in the future. If you're interested in future projects like this, you can subscribe to Lapse Laboratory and it helps me out a lot. If you really want to help me out, leave a comment and a timestamp with your favorite shot from this entire project. I debated on a number of ways to try and fix all the shells floating out of solution without putting anything on top of them because that would ruin the upcoming overhead shot. I also hypothesized that the 5% vinegar potentially might not have enough buffering or reaction capacity to actually dissolve all the shells in the beaker. I was hoping that the shells still submerged would dissolve and that the eggs positioned on top of the dissolved shells would continue to push down on the now shellless membranes that would be less buoyant, eventually causing all the shells to dissolve. But that didn't seem to be happening, so in a few moments here, in order to try to dissolve all the shells, I added the 75% vinegar solution to the beaker to see if the higher concentration would more rapidly dissolve the remaining calcium in the eggshells. You can see a single frame of me adding the higher concentration acetic acid at the 134-hour mark. Interestingly enough, it caused a white precipitate in the beaker and made the entire solution not nearly as clear as the 5% solution, although it did rapidly dissolve the remaining calcium in the eggshells that were submerged. You can see the self-collapsing motion I mentioned earlier occurring after this was added. You can also see how the intensity of the reaction picked up, and you can see the massive floating membranes all bunched up around the 900 milliliter line. You can also see the membrane's paper-like texture being moved around by the CO2 bubbles in a way that wouldn't have occurred if the shells were still present. I really wanted all the acetic acid to dissolve all the eggshells and leave behind only the membranes, but it was clear I would have needed to set up this shot differently to get that to happen. After 12 days, I was happy with the amount of shells that had been dissolved. I didn't think with much more time that much more would happen. Here's a top-down view of the project, and you can see how quickly the eggs get pushed out of the beaker, as well as you can see a lot of the precipitative acetic acid that forms crystals along the ridges and edges of the shell. I found the crystal growth along the cracks very interesting, and I'll probably film more crystal growth on this channel at a later date. You can again see the self-collapsing motion I was talking about earlier in action here, where the heavier, non-submerged shells are feeding back into the vinegar and being dissolved. From this top-down view, the thing that I found most interesting was the formation of crystals on the top right shells. The crystals form, then reach a peak height, and then fall back into the solution. You can also see from the angle the cracks in the shell that are building up their own acetic acid crystals. I also thought it was interesting to see the crystal growth along the edge of the beaker itself, specifically along the left side of the beaker after the 75% solution is added. In that shot, you can see the crystals begin to bubble up and form along the rim of the glass. You can clearly see the floating shell membranes on the left side of the beaker. As more water evaporated out of the solution, you can see more and more crystals forming all over the beaker, shells, and even on top of some of the floating eggshell membranes right above the liquid. On the left-hand side, you can actually see a crystal grow and then fall back into the liquid. If I were to set this up again, although I had enough space in the beaker to dissolve all the eggshells, I would most likely need to add the vinegar in stages instead of all at once if I wanted to dissolve everything. But that would have also changed the framing of the shot and introduced another level of complexity in filming, which isn't necessarily a bad thing. It's just something I would have had to consider early when setting up this shot.
So after nearly 2 weeks of filming, this took considerably longer than I thought it was going to take because I didn't wait on the top of the eggs. So if I'm going to do this again, I need to remember to make sure that the eggs don't just float up out of the vinegar. But did get a really cool precipitate that formed here.
This shot's really great because you can clearly see the precipitate at the ridges and cracks of the egg. Seeing the crystals grow out of the surface crack of the egg was pretty unexpected for me.
And you can see even some places where the eggshell got pushed out of the beaker during filming. And there's some of the deposition on the shell. And then what's left here is just a bunch of membranes. So this is not soluble in acetic acid or vinegar. And so it's just these thin membranes that are left after the eggshell dissolves.
I thought the color difference between the membrane and the egg was also interesting, with the membranes having a much more yellow tone versus the eggshell. I wasn't sure if this was an effect of the vinegar or if this is actually closer to their normal color once they're removed from the eggshell. Here I'm draining off all the excess acetic acid, vinegar, and water from the solution. Because the solution is mostly the 5% acetic acid vinegar, the smell of the gas coming off the beaker isn't overwhelming.
You see that most of what's just left is just the membranes of the eggs. And where the egg was out of the solution, it's still hard and has that precipitate on it. And see you here. Part of the egg, it's just the membrane, and there's still a little bit of that hard shell there.
I really struggled to come up with an analog for what the membranes feel like coming out of solution. They have a smoothness to them that I can almost describe as the surface of a wet sheet of rubber. They do have some of the spring of a rubber, but they tear like a wet sheet of paper. It feels almost like the thinnest piece of tofu you could ever possibly slice, and after moving it from the beaker, it actually has a similar weight to something like a wet tofu, while still having a little bit of that stronger vinegar smell due to the presence of the 75% vinegar that we added later in the solution. There's enough liquid present in the membranes that I can just squeeze it out onto the tray here.
Just completely soft in just the membranes of the eggs.
The membranes pulled apart incredibly easy after taking them out, and it was interesting to see some of the membranes that were still connected to undissolved sections of the eggshell. There was almost a thinning down of the eggshell, and it would eventually transition into the thin membrane. I found it really interesting that there wasn't just a hard cutoff between the two types of material.
See the egg that fell off.
These eggs have been sitting in my refrigerator for 15 months while I edited this footage, and in that time they've become completely desiccated and hard. This is the egg that ended up floating out of the vinegar, that never got shrunk with corn syrup. This is the egg that was in the 5% vinegar solution. Interestingly enough, they still have a faint vinegar smell even after all that time. This was the egg in the 75% vinegar solution. They almost feel brittle and like they would shatter very easily. I'm a bit surprised they still have a smell, being as solid and dry as they are. Overall, I had a great time shooting this project, and I'm looking forward to shooting more time-lapse on this channel. And I've got some really great stuff that I'm filming right now. If you want to support the channel, you can subscribe on YouTube, or you can follow me at the social media links at the top there. If you want to support me even further, you can subscribe to Lapse Laboratory on Patreon. On Patreon, you can see behind the scenes of projects I'm currently working on, you can ask questions, and help me create new projects. And as always, thank you.